Section 10.3 is called arc length and surface area in parametric equations. And we're going to start with the arc length. Now, you have found arc length before. You did it in Calc 2, I think. And you did it, of course, for a function that was in, or it did it for a function. And now we're going to do it for a parametric equation. So if we have a curve that's defined parametrically by x equals x of t, y equals y of t, it goes between the points a and b. We've got continuous derivatives on the interval ab. And last time we actually saw a definition similar to this, but it actually said that they started and ended at the same point. We found area between them. Do you guys know what I'm talking about? The last sets of problems you're doing on your homework? Okay. This one doesn't have to start and end at the same location, and it actually can cross itself as well. It could cross itself at a finite number of points. So it's got this additional sort of ability to calculate in spite of some crossing over things. Then the arc length of the curve is actually given by this formula. And we have seen this formula before, right? It's the Pythagorean theorem, right? I mean, that basically, or the distance formula we talked about last time. So this is s equals the integral from a to b, and we've got that square root that we saw last time. And we are going to take a look at some examples of this. Do you have your calculator out? Because you will need it very quickly, too. Not on the first part of the example, but on the second part you will. Okay, does everybody have this one written down? We're getting close. All right, this is the example we're going to use. And notice the directions, and this is exactly the directions you're going to see in your textbook. It's going to say, find the slopes of the tangent lines to the given curve at the indicated points. What happened? That's not the directions. Hang on just a second. Yes, it does. Okay, we've got a problem. I copied and pasted the wrong things. All right, I'll just fix them. That's okay. Your directions are the right on your paper. It says find the arc length of each curve. I need the exact number of slides that are written here, too. You're right, I am. Well, that's going to have a cross on it, too. The part that's incorrect, of course, is the directions. We're going to find the arc length. Notice the other part of your directions, which is kind of funny. It says compute one exactly and one approximate the other numerically. So there's going to be one of the two problems, and each one is going to have two parts. So in the paper that you've got one problem, part A, and then you've got question number 1, part B on the next page. So these will occur in pairs in your book. One of them you will be able to actually compute the antiderivative. The other one you won't. Okay, so they're kind of giving you a little bit of a heads up, is that sometimes this is actually able to be found, and sometimes you can't. And so they're going to give you one of each in each numbered problem you have. So when you're actually looking at the homework set, there's going to be 3 of these problems, but it's really 6 of them because there's an A and a B, and you're doing both parts to it. Okay? So be aware of that. All right, so the directions indicate, so I've got the wrong directions, but I've got the right equation, right?
Yeah.
Okay, well that's good. All right, so my directions are just wrong. All right, so in this formula, what do I need to do in order to compute this? I'm going to need derivatives, yeah. So let's find the derivative of each of these pieces first. So what is x prime? Oh, it's a product rule. You're right. That's a good thing to notice. All right, I'm hearing something like this. Sine of t times the negative sine of t plus the cosine of t times the cosine of t. Does that sound like what you got? Okay. Let's take a minute just to clean this up. I'm going to write it as the cosine squared first, just so that my subtraction's in the middle. It doesn't much matter, but that's how I'm going to choose to write it. Okay. How about the second one? What is the... Oh, I'm sorry. I left the squared off. Yes, thank you. All right, what is y prime? Good. So that one's a chain rule, right? You bring the 2 down and so forth. Okay, any questions so far? Okay, so we're going to set up our integral. Our integral is going to be going from 0 to pi over 2 of the square root of the cosine squared of t minus the sine squared of t squared plus 2 sine of t cosine of t squared dt. That look okay? Now, nice things are going to clean up. I mean, these have been created to do wonderful things. I mean, that's why the problems are created the way they are, is because things are going to drop out and simplify for us. Even in the one that we're going to end up using the calculator to finish solving, things are going to clean up before they finish solving. So we don't know if we need the calculator yet because we haven't simplified anything. So we are going to simplify this as our next step. So what am I going to get when I square these things out? First, I've got cosine to the 4th, right? What's my middle term going to be when I FOIL? It will be. There will be a cosine squared sine squared. Good. Minus 2 cosine squared t sine squared t. And then my last term will be positive sine to the 4th of t. What about when I square the 2 sine t cosine t?
4 sine squared cosine squared.
Excellent. Now, cancel out probably wasn't the right phrase before, although it could have. This one does simplify, though. These two pieces can combine, right? Yeah? I mean, they're the same. And because they combine, and the way they combine, it's actually quite friendly. So bear with me for a moment and take a look. This would be cosine to the 4th of t. And then I've got plus 2 cosine squared t sine squared t. And plus sine to the 4th of t. Okay, does that look okay? Is that what everybody has? What would you do at this point? I know it looks really messy, but this factors very nicely. Or unfoil, yeah. It looks just like what I got over here, except for what? It's positive 2. So it's going to factor just like it did here, except it's going to have a plus sign. So I've got the integral from 0 to pi halves of the square root of cosine squared t plus sine squared t squared. Now, let me make one comment before we notice something very helpful here. At the very least, the square and the square root cancel, correct? But this has more than that going on. What?
Cosine squared.
Yeah. So this piece actually equals 1. And like we said, these also cancel, even though it won't matter because I've got the square root of 1, of course, and then 1 squared. But this ends up becoming the integral from 0 to pi halves of 1 dt. So, what's the integral of 1? No. X, or t, because we're working with t here. Pi halves to 0, right? So what does this end up working out to? Pi halves. Now, we did in class last time, and we'll do it here just a minute anyway because we'll need to. But if you simply wanted to verify that you had this correct, you could come back to where we even very first started, even before we squared things if you wanted to. You could put this exact expression right here into your calculator, and you could do math 9, right? Like you could check yourself if that's something that was concerning to you. So you don't have to. But you could. Now, you're going to need to do something like that on this problem. So I didn't mean to cross these out. Apparently, it was just my directions that are messed up. All right. All right, so same directions. And based on the fact that I was able to solve the last one without using the calculator, the way the directions are actually phrased, we know we're going to need it for this one. Agreed? because they're saying in every problem number they give you, they're going to give you an A and they're going to give you a B. One of them you can do by hand, the other one's going to require the calculator. That does not let you off the hook on the simplifying, though. We're going to simplify it down to the point where we have to use the calculator. Okay? Everybody with me on that? Okay. We're going to start the same thing we did last time, though. Where do we start on these particular problems? Derivatives. And we have two product rules this time, don't we? All right, so what in the world is the derivative of sine 4t cosine t?
4 cosine squared plus minus.
Okay, I'm going to write it out with, I don't think we get to do cosine squared. Why not? One of them's got an angle 4t and the other one's got an angle t. Yeah. All right, so we are going to have a product rule, and we've got a chain rule in there too, just like you said. So I'm going to have something like that. Negative sine of 4t cosine of t plus 4 cosine 4t cosine t. Did you get all the pieces in there right? Is that what you guys have?
That's what I think.
Yeah. No, it should be minus sine of 4t, sine of 4t.
Oh, yeah, it should be sine t.
You're right. So that's what's written on paper too, and I copied it down wrong. Good. Okay, does that look okay now? Good job. All right, we're going to do the same thing on y prime. Notice I can't simplify that. Just like we said, there's no, I know I've got sine times sine, but they're different angles. I shouldn't say I can't simplify it, but let me just tell you this. When I was working through this problem last night, I'm going to do it the way that I did initially, and I didn't like it very much, and so I tried something else, and it was far worse. So there are ways to simplify this expression, but they actually don't end up helping us as we work through the problem. So we can use trig identities to simplify this, but it actually creates more of a mess later. So let me just clarify. There are things we could do, and we will do some of them later, but it's not going to help us right now. Okay, how about y prime? Somebody tell me what you get for y prime.
4t cosine t.
What's next, Jordan?
4 sine t cosine 4t.
Okay, did I hear you right? Did I get those pieces in there?
Right.
Excellent.
Is it 4 sine of 14?
Up to the left.
No.
Nope.
Oh, cosine.
I do have a sine of 4t, but it's at the beginning. The cosine of 4t is at the second part of it. Do you get the feel, looking at this, of why I would have liked to simplify this now? What am I about to do with this? Lots of foiling, squaring things. And I'm going to be squaring things that have components that are multiplied, right? So this is going to be very long. I mean, like lengthy in terms of writing it down. I'm going to have lots of pieces. All right, so that's where we're headed. We're going to do the arc length, which is the integral from 0 to pi halves. And my square root is going to have negative sine 4t sine t plus 4 cosine 4t cosine t squared. And I know this is terrible notation, but I'm going to write it all underneath the square root like this because my screen's too short. I can write it across the paper, but I can't write it across the screen. And then I'm going to write the other piece, sine of 4t. So these are not numerators and denominators. It's just a continuation. Cosine t plus 4 sine t cosine 4t quantity squared dt.
You just integrate that by our
No. I mean, yes, you can, but no. So, nope. This is your class period where you get to exercise your trig skills. Okay? Oh, you guys are going to be great. All right, so some of this is pretty easy, right? The squaring part. So this is sine squared of 4t, sine squared of t for the first piece.
not want to do this one.
I'm foiling. So I'm taking this squared and I'm going to FOIL out the first piece. Is that okay so far? So the negative goes away because it's times itself. Agreed? Now, we're going to do the same thing we did on the inside of the last one, where we multiply the two terms together and double it, right? So that's going to give me -8 exactly. Whoops, let me keep it in black. -8. And then I'm going to have all four of these terms because none of them match, do they? Sine 4t, sine t, cosine 4t, and cosine t. Everything's going to clean up really quickly after this, okay? It's just one step of mess. Okay, maybe 2 steps. The last step was kind of a mess, too. What else do I have? Oh, cosine 4t, cosine t. What's my last piece here?
4 cosine squared 4t, cosine squared
Is it 4? It's 16. Yeah. 16. It's okay. Cosine squared of 4t, cosine squared of t. And for the record, I can't fit any further than just that across my page actually written down either. So my actual notes that I'm working with up here actually do exactly look like I'm about to write on this screen. They look like a double stacked kind of thing underneath this radical because I ran out of space, and I suspect many of you do as well. Let's do the second piece. We're going to square the second piece down here, right? So what do I get when I take this second piece and I square it? Well, there's sine squared of 4t, cosine squared of t. Agreed? What's my middle term going to be? Plus 8, what? Yeah, all of those multiplied together, but if you notice, they're the same 4 pieces. Sine of 4t, they're in a different order. Cosine of t, sine of t, and cosine of 4t. They're exactly the same 4 pieces as then the problem, or not the problem, but the portion that's above it. Like these two, they match, except that they're opposite signs. So they're going to add to 0, right? Already the problem's starting to look better. Okay? These pieces are going to go away. All right, what's the last part going to be? 16 again. Sine squared of t and cosine squared of 4t. Okay, take a look at what is left now. I marked out the red pieces. Those aren't there any longer. What? Oh, yes, you're exactly right. I'm out of space. I wouldn't have forgotten it if I didn't have any, if I had any space left. You're right. Okay. Okay, look at the pieces that are left, though. What can you tell me about, let's just look at them where they are currently. What can you tell me about that first piece right here? These two, when you compare them. No. You can't add them. They're not identical, but do they have something that's in common?
Sine squared 14.
Yeah, they both have a sine squared of 4t. And what did I hear? Jordan, what did you say? You can factor out that piece that they have in common, right? And then the pieces that are left add to the number 1. So I'm going to actually show that out so you can see it, because some of you are looking at me and you didn't quite catch what I said. But that's exactly right. So I can take out the sine squared of 4t, and what I'm left with is sine squared of t plus cosine squared of t, and that value is equal to 1. So this piece right here equals 1.
Is that the very first piece you took out?
That is the very first piece. Over here, it's the part that's highlighted in blue. They both had a sine squared 4t in them. So I factored that piece out, and the pieces that are remaining are the sine squared and the cosine squared. But take a look at the last piece. You can do the same thing, right? So we're going to take out a 16 cosine squared of 4t, and we'll be left with cosine squared of t plus sine squared of t dt. And again, we've got that piece equaling 1. So now I have sine squared of 4t plus 16 cosine squared of 4t. They don't equal 1, obviously, because I got a 16 in front of one of them and I don't in front of the other one, so that's sort of unfortunate. However, I can change one of them so that it looks like the other one. Since the first one is not multiplied by 16, that's the one I'm going to pick to change. But if you change the other one, it would be fine too. This sine squared right here. Do you remember how you could rewrite sine squared in terms of cosine? Close. It's 1 minus cosine squared. Yeah, so we're going to rewrite this. So this would be 1 minus cosine. I have left off my integral. Let me put that back in there. So 1 minus cosine squared of 4t plus 16 cosine squared of 4t dt. So you're using those Pythagorean identities, right? All right, so the last and final step, the last thing you can do is you can write this then as 1 plus 15 cosine squared of 4t dt.
Yeah, wouldn't it get rid of the sine cube, 4t sine cube t?
What was that?
From the last slide,
Mhm.
very first thing, you had sine cube, 4t
It's
sine-
not a cubed, it's a squared.
Oh,
This is a squared, just like this one. Yeah.
so what we do
Sorry, it
with-
looks a little
what we do
sloppy.
with those first ones,
We factored it out. These two pieces matched, and so we factored them out in front. They were added together, so we did a factoring step. We said, since I'm adding these two pieces together and they have something that's alike, I can factor that piece out. So then what means is that I have this piece and this piece left of the factoring with a plus sign between them. So it turned into this right here,
Gotcha, okay.
all of that. And we did that same thing basically twice in two parts of this particular expression.
That makes sense.
Yeah. Grab your calculator. Because you can't do that one by hand at that point. You are done. There's no more simplifying to be done. And to be honest, that first expression where you had all the squareds, you do not want to enter that in your calculator anyway. The likelihood of you making a mistake in entry is probably higher than not. I mean, seriously, you're going to have parentheses all over the place. Your squared is going to end up squaring the angle instead of the sign. Something is going to happen. It's not going to enter right. There's too much going on. So the simplifying that you're doing is also going to help you in doing the entry correctly. So the only thing you need to enter then is the square root of 1 plus 15 cosine of 4t, quantity squared. Most of your calculators will do something like this, and they'll make you put the squared right out here, or some variation of that. That's what my calculator, my 83X, makes me do. And then a reminder, we did this last time. You can do this in function integration. This is in Math 9. So if you press Math and choose option number 9, you get this thing that says FNINT. The notation is to put in the y1 variable, which you get underneath the variable button, which is, it says vars. You tell it x, which is your variable. You put the lower limit. For us, that's 0, and then your upper limit, and for us, that's pi halves. And then you press enter. This is the notation. This notation occurs in your regular screen after you've entered this piece into y1. You guys get values yet?
4.29.
Yep. If we're going to go 2 decimals, so just what we were doing last time, we do 4.29.
No, you didn't.
I got it. That's what I got.
Okay. Let's take a look. Oh, you've got 89. Let me see. First day to entry. You're going to start there.
Are you in radians?
That's a good question.
I just got it.
You didn't square the 15 cosine 14. Well, square. You didn't square the cosine. Yours-
Oh,
You did okay?
cosine.
The cosine is 4t. All of that is then squared. So it's cosine squared is the angle. So we're squaring the cosine of 14.
It's just cosine squared 4t. It's not cosine squared 4t squared.
Right. I scratched out the square there because most of the
Okay.
calculators make the square on the outside. Okay. Did anybody else not get a 4.29? Are you getting 4.29 now, Joel?
No. Well, yeah. I hit that wrong again.
Did you tell it from 0 to pi halves in here somehow?
Wait, I'm differentiating.
You're differentiating. Well, certainly not going to work then. All right, give it another try. We'll check it in a little bit. If it's not still working, you let me know, okay? All right, any questions on this? Okay, so that one's good? I mean, it was a mess, but we're all good now. All right. The other fact that we're going to work with in this section is surface area. And when we talk about surface area, what shapes are we talking about? What kind of a shape has a surface area?
All shapes.
Ball shapes, they do. What else?
Oh, I said all
No,
shapes.
all shapes do not.
What kind of?
Well, I mean, if you had one that was infinitely thin, I guess it would.
Okay.
What do you got?
What kind of a shape can we talk about surface area for? 3D shapes, that's what we're looking for. Something that's three-dimensional. If it's not three-dimensional, it doesn't have a surface area. You can talk about its area, but not its surface area, right?
Tomatoes fine.
So the things that should be coming back to your mind is things from Calc 2 that looked like solids of revolution, disks and washers.
Oh, we're not doing that.
We're not doing that again. But you know what? The Calc 2 class, the Calc 2 class is doing it today, yesterday, and tomorrow. So
Nobody likes
I do. I love those.
all right. Well, if you love them, you should probably talk to somebody in Calc 2 because I suspect that tomorrow they're not going to love them.
Oh.
So, yeah, isn't that fun? So we're going to look at surface area. The surface area and what we're working with in our section with parametric equations is much easier to deal with, okay? There are two different equations. One is around a line y equals c, so in other words, a line y equals, and one is around a vertical line x equals d. Okay, there's nothing special about c and d, they're just numbers. And the pieces that we have are coming from, again, that arc length, right? This right here, you see that arc length piece right there? And then this piece right here is coming from the radius, how far away it is from the line that you're rotating it around. So we're not even going to draw in 3D. Okay? Now, for those of you who enjoy drawing in 3D, take Calc 4. We will draw in 3D in Calc 4. Okay? And you'll get to see my terrible artistic abilities. So we'll do some 3D stuff there. But for now, these equations will work very nicely. Okay? They're very clean. So jot those down for us. And they're almost identical, right? The only difference is the radius piece here. And that is dependent upon whether you're working around a line that's a vertical line or horizontal line. So this one right here, y equals is horizontal. And of course the x equals is vertical. And if you're interested in the 3D shapes, your book actually draws some beautiful 3D shapes as it discusses this, but you don't need the shape in order to be able to do the problems. Okay? Okay, did everybody get everything written? Excellent. Let's take a look at the couple of examples here. It's the same example, that is, we've got the same functions, x and y, the same parametric curve. We're just rotating it around a different axis. Even the limits of integration 0 to 2 are not going to change. It's just the axis that's going to change. Okay? So first of all, let's take a look and talk about what in the world this axis is telling us. If we're rotating it around the y-axis, what's the equation of the line of the y-axis? This is x equals 0. Okay? Which means we're looking at the second case right here for the surface area, right? It's an x equals line. So far, so good? Yes? Some of you are giving me funny faces. Are we good? Okay. All right, so we need what? What do we need to do in order to do this problem? Derivatives. Are these a little easier to deal with than the last problem? What's the derivative of x? 3t squared minus 4. How about the derivative of y? Excellent. Can't do hard problems all the time, right? Man. All right, so we're going to find the surface area. The surface area is found by the integral. Our limits of integration are from 0 to 2 of 2 pi. And if you want to put the 2 pi in front, that's fine as well. That's giving you the rotation, right? 2 pi around a circle. I'm supposed to have the absolute value of x of t. Well, the absolute value, x of t minus the x value I'm rotating around, but the x value I'm rotating around is actually x equals 0. So this ends up just being the absolute value of 3t squared minus 4. And think with me on this. This goes, oh, I'm sorry, you're right. I wrote an X, even said it. Take a look at this. If the t-value of this, I know we don't evaluate inside of this, but think about what's happening here. If the t-value is 0, what's going to happen inside of this absolute value? It's going to be negative. And if I go up to a t-value of 2, I'll get to a positive at that point finally. So I do need these absolute values to be happening to make this work.
Is that supposed to be X?
Yeah, is it supposed to be the
The original. I was like, something's wrong. I should have the original because it should be a negative the entire time. Yeah, you're right. Look at my notes and I missed that piece. TQ minus 4t. Let's think about it one more time then. If t equals 0, I get 0 for everything, right? If t equals 2, what do I get?
0.
I get 0. So this one's actually going from 0 to 0. What's about in between? What if t equals 1? It's negative. So actually it starts at 0, it ends at 0, and it's negative everywhere between. That's what's going to happen on this one. So when I take this absolute value, I'm not going to actually do it. I'll show you how it affects your answer when we're done. But if I were to take this absolute value and actually look at whether or not I need that there, right? If it's positive everywhere, I could just remove it. If it's negative everywhere, I could just change the signs. If I actually wanted to actually simplify this, I would change the signs. Yes? Do you have a question, Joel? No? Okay. All right. Our last piece then is the square root piece. So the square root of 3t squared minus 4 squared plus 2t squared dt. All right, so my integral from 0 to 2 of 2 pi, I'm going to leave the absolute value as it is, but like I was saying just a minute ago, if you wanted to, you could actually just reverse the signs and pull the absolute value off. I wanted to leave it there because I want to show you how it affects your answer in the calculator in a minute. Let's simplify what's underneath my radical. What do I have? After all the squaring that we did a minute ago that was tough, do something easy for me.
We have 9 to the 4th.
Minus 24t squared.
Good. 24t squared.
16 plus 4t squared.
Excellent. And part of this will simplify inside there. Not a lot of it, obviously, but a little bit. So what am I going to get inside or under the radical? 9t to the 4th minus 20t squared plus 16 dt. All right. From that point, there isn't any other simplifying that we can do. We can't clean up the inside. It doesn't factor and then square roots cancel or anything like that. So what are we going to do? Yeah, you're going to use your calculator to find the approximation. Yes, you are. And you're going to do that on any of them that don't have the ability to actually find the value. And I think I checked them, and I think that's all of them, but I could be wrong. So you do need to simplify them to make sure of that fact, but I'm pretty sure it's all of them on this. So in your calculator, you don't need to worry about the absolute value for now. Just put parentheses there where you see the t cubed minus 4t. Then it'll be fine. I just want to show you what would happen if you didn't. So you can leave yours in there, Caleb. Somebody else use parentheses instead of the absolute value signs there, because I want you to be aware of what happens differently if you sort of gloss over the fact that those were there, I guess. We're going to integrate this, of course, from 0 to 2 and get an approximation. So when you get there, somebody tell me what answer you're getting. What answer did you get if you put the absolute values in there, Caleb? 8.2?
Yeah.
2 decimals. So somebody who didn't put the absolute values in there, what did you get? You get negative 85.282. Yeah, it's just the opposite sign because you neglected the sign to begin with. Can area be negative?
No.
No. So there's a good key of what's going on. Anti-area. All right, so we get 85.82.
Wait, so So it won't let you do the absolute value?
It won't let you, or what are you asking me?
Is that what you just said?
If you do the absolute value in there for around the t cubed minus 4t piece, you'll end up getting the correct answer, which is 85.82. If you just do parentheses, your answer will end up telling you that it's negative 85.82 because you didn't do the absolute value. I mean, that's what's happening, is the absolute value piece is missing. So you still would recognize that you had the answer. It would just be the wrong sign that the answer gave you. All right, let's do the other one really quickly. We've got the same derivatives, so we don't need to redo those. And this is about the line y equal 2, which means I'm using the other formula that was given on that surface area slide. So I have 2 pi. I'm supposed to be taking the y value, which was t squared minus 3, and then subtracting the value of 2. And then I have the same square root that I had before. There's no need to simplify it again. I already did that once, right? So you're just going to reuse it. The piece that's changing, of course, is this piece when the absolute value is in the middle, and it's t squared minus 5.
Don't you use y of t not x of t though? That's what you have.
Y of t right here.
Never mind.
Oh, you were looking at this
Yeah,
equation,
I was looking at the
Yeah.
derivative.
the derivative of x, yeah. So we are using y of t, you're right. So we're using the t squared minus 3, and then we'll subtract the 5. And then you might be able to, depending on how you did the problem already in your calculator, make a few changes without actually rewriting the whole thing to change this to be t squared minus 5 in the absolute values. The same thing is going to happen as happened before. Somehow I turned it into a pi as my upper limit. That's fun. Maybe I should fix that. At 0, the absolute value is going to actually have a negative value inside of it. And at 2, it will as well. So this is actually negative the whole time. So if you enter it without the absolute values, it's going to give you that negative value. And if you enter it with the absolute values, it will write it down properly as a positive value. What do you get for your approximation? 162.60.
Why did you minus 3 minus 2 again?
It's part of the formula. I don't have my parentheses in here to indicate it, but it's the y of t minus the value y that we're rotating around,
Yeah.
which was the 2 there.
It's subtraction, not minus.
It's subtraction
What'd I say?
minus.
Why don't you want to slot an action for 2?
All right, any questions?